In all the numerical examples of the application of Newton's second law that we have studied so far, only the motion of one object was involved. The net force was calculated as the sum of all the external forces exerted on that one object, even if I did not remind you that those forces were meant to be external. In contrast, internal forces are exerted between parts of an object and are not part of the summation that leads to the net force on that entire object. To evaluate internal forces using Newton's second law, a change of object is required. We need to turn an internal force into an external force. Let us look at numerical examples to illustrate how this can be done. This example involves 3 boxes in a row on an icy level surface. To simplify matter, no friction will be involved in this first example. An applied force is exerted on the box which is on the left side of the row of boxes. We are interested in evaluating the contact force between the 2 last boxes. We will use this set of reference directions. The givens include the masses of each box, and since they are placed in decreasing order of mass from left to right, we have that M1 is equal to 8 kilograms, M2 to 5 kilograms, and M3 to 2 kilograms. The magnitude of the applied force is 55 Newton. Since the motion is strictly horizontal, none of the boxes have a vertical component for the acceleration. The reference to icy surfaces in physics often means that the friction is considered negligible. Since the 3 boxes are sliding as one unit, they all have the same velocity, so they all have the same acceleration. Let us start this problem by finding this common acceleration. And we will consider the motion of the 3 boxes as one object. They each have a weight. They are all touching the ground, so they each have a normal force. And since there is no vertical motion, all the normal forces are canceling the weights, so that the net force is due to the applied force. Applying Newton's second law to the x component for the entire set of the 3 boxes means this expression. And there is only one horizontal force, so the x component of the net force is Fa, due to our choice of reference direction. Isolating for the x component of the acceleration gives this expression, which is also the expression for the x component of the acceleration of each box. Now to the task of evaluating the contact force exerted by mass 3 on mass 2. When we were working with the object being the set of 3 boxes, this contact force was an internal force because it was exerted between 2 parts of the object. To evaluate it, using Newton's second law, we need to define a new object that does not include both M3 and M2. If we define our new object as M2 only, its contact force with M3 is now an external force, but so is the contact force with mass M1. I didn't want to label these forces as normal forces, even though they are normal forces, because we had already used that notation for the contact forces with the ground. Here, SPHU3 means the contact force on mass 2 by mass 3. Using Newton's second law would give one equation with 2 unknowns. We would need an equation to evaluate Fc21 as well. Not an impossible task. We just need to apply Newton's second law to mass 1 only to get that second equation. But let us look at a different approach. What if we apply Newton's second law to M3 only? This time we have only one horizontal force, the contact force on 3 by 2. But it is not exactly what we are looking for, we want the contact force on 2 by 3. But we can appeal to Newton's third law that states that the force exerted on 2 by 3 is equal in magnitude but opposite in direction to the force on 3 by 2. In this second approach, we also end up using two equations. To be very contrarian, I'm going to go for a third approach, the one where our new object is mass 1 and 2 together. We still have the contact force that we want to evaluate. The contact forces involved between mass 1 and 2 are back at being internal forces. The other horizontal force present is the given applied force. This time, if we applied Newton's second law for the combination of mass 1 and 2, we get this equation. Replacing the x component of the net force with the sum of the x components of the forces present gives us this. The x component of the applied force is the magnitude of the applied force, and we also can use the previous result for the x component of the acceleration. Isolating for SPHU3, which stands for the x component of the contact force on mass 2 by mass 3, gives this expression. Factoring out Fa from the two terms to the right and doing some sum of fractions leads to this final expression for SPHU3 in terms of the givens. We have reached the stage of being able to substitute the numerical values of the givens and to use a calculator. The negative sign indicates that the x component of the contact force is opposite to the reference direction, so the final answer is minus 7.3 Newton x hat, or 7.3 Newton towards the left. This next example is our last example on the subject of forces. It involves kinetic and static friction forces and the need to clearly define the object that we will be working with. It consists of two boxes that will slide horizontally along the floor. The bottom box has a mass of m1 and the one above a mass of m2. An horizontal applied force is exerted on the bottom box. We will use this set of reference directions. We need to find the range of values for the applied force that will result in the sliding of the two boxes as one unit. The range will be governed by the maximum static friction forces. The minimum applied force must be higher than the maximum static friction force due to the contact force between the bottom box and the floor. Otherwise, there will be no sliding. The force responsible for M2 to be able to keep up with the box M1 is a static friction force between the two boxes. Its maximum value will set a maximum value for the applied force. Let us see how we can evaluate all that. First, our list of givens is the mass of the bottom box, the mass of the top box, the coefficient of static friction for the contact force between the two boxes, and the coefficient of static friction for the contact force between the bottom box and the floor. The subscripts 2 and 1 are used to differentiate between the two coefficients. The material of the box 2 is not the same as the material of the floor, resulting in two different coefficients of static friction. We also have the coefficient of kinetic friction for the contact force between the bottom box and the floor. The motion is strictly horizontal, so the vertical components of the accelerations are all zero. Let us start by evaluating the minimum value for the applied force. We will define our object as the two boxes together. The free body diagram includes the applied force already shown, the total gravitational force, the normal force exerted by the floor, and the kinetic friction force present when the object is sliding. Application of Newton's second law for the vertical components gives this. The only vertical components are for the normal and the weight, which can be replaced with Fn1 and minus m1 plus m2g respectively, and which leads to the magnitude of that normal force to be equal to the magnitude of the weight of the two boxes. With the normal force, we can write the expression for the maximum value for the static friction force and replace Fn1 with what we have just established. This maximum value for the static friction force gives us the limiting value for the applied force necessary to start the object sliding. So our applied force needs to be above this limiting value. Substituting the numerical values for the givens gives this, and the use of a calculator gives that. We now have our lower limit for the applied force. Now, working with the two boxes sliding, let us apply Newton's second law to the x components. The net force includes the applied force and the kinetic friction force, and their x component can be written using their magnitude. The next step is to use the expression for the magnitude of the kinetic friction force in terms of the normal force. After that, we can substitute the expression for the magnitude of the normal force. Isolating for Fa gives this expression, which relates the horizontal component of the acceleration to the magnitude of the applied force. Isolating for Ax instead gives this expression. But this is not over. We have to make sure that the two boxes are moving as one unit, which means that both boxes need to have the same velocity and the same acceleration. The two boxes cannot be sliding in respect to each other, so if friction needs to be present, it has to be a static friction force. Let us apply Newton's second law to box 2 only. The free body diagram would include the gravitational force exerted on mass 2, the normal force exerted by mass 1 on mass 2, and the static friction force to accelerate mass 2 towards the right. Now let us apply Newton's second law to the vertical components. The only forces with vertical components are the weight and the second normal, which can be expressed in this fashion. We finally have that the normal involved with the contact force between the two boxes is m2g. Since the upper limit for the magnitude of the static friction force between the two boxes is given by this expression, we can substitute Fn2 for m2g. Next, we will work with Newton's second law applied to the x components. The only horizontal force on m2 is the static friction force, and we can also use the expression for the x component of the acceleration that we have derived earlier. Due to the set of reference direction, the x component of the static friction force is the magnitude of the static friction force. Fs2 needs to be smaller or equal to its maximum. Let us now isolate the magnitude of the applied force in this inequality. We have reached a stage where we can substitute the numerical values for the givens and find the numerical value for the upper limit of the range. Combining the result from before, we can write the final answer. I know that we have reached the final answer and I could stop here, but I would like you to notice why we were able to find a range of values for Fa. According to the expressions for the lower and upper limits, the lower limit is lower than the upper limit only if mu s1 is smaller than the sum of mu k1 and mu s2, which was the case in this example. This concludes our study of forces. Our next step in quantifying the physical world is about defining the concept of energy, and more particularly, the concept of kinetic energy. This will be the subject of the next installment.